everyone again for joining. My name is Clara Deck. I'm with the NOAA Climate Program Office. This webinar is part of our series highlighting research from recent and current fellows in the NOAA Climate and Global Change Postdoctoral Program, or the C&GC program. The C&GC program is sponsored by NOAA's Climate Program Office and managed by UCAR's Cooperative Programs for the Advancement of Earth System Science. Today we have Melissa Breeden joining us to present her research titled Subseasonal Precipitation Forecasts of Opportunity over Southwest Asia related to ENSO and the MJO. Melissa was recently a C&GC fellow at the NOAA Chemical Sciences Laboratory, where she studied the variability of deep stratosphere to troposphere exchange. Melissa is currently pursuing subseasonal to seasonal prediction of variables relevant to hydroclimate in her current research. And we will have time at the end for questions. So please use the questions feature within GoToWebinar to ask your questions, or at the very end, you can use the raise hand feature and I can unmute your microphone so you can ask your question directly. So without further ado, I'll hand it over to Melissa to begin her talk. Thanks for joining.
All right, thanks Clara so much for that introduction, and thanks everyone for tuning in. So yeah, that's what I'm going to talk about today, subseasonal precipitation forecast of opportunity. And we're focusing on Southwest Asia, circled here, and with a focus particularly on Afghanistan, if I can, yeah. There we go. So there's Afghanistan, where we have lots of concern about food insecurity in that country, and several of these other countries are rather food insecure as well. So I'm a research scientist at CERES, which is a cooperative institute. I sit at the NOAA Physical Sciences Lab, which is where I am in my office right now. And then I'm supported by FuseNet, the Famine Early Warning Systems Network. So I'm just going to briefly go into what FuseNet is, in case you're not familiar. I was not until I got this job, and how our weather and climate outlooks are assimilated into this bigger question of food distribution and humanitarian food distribution in particular. And then I'll jump to the more science focus, first giving a little bit of background on the current state of subseasonal forecasting, introduce the tool we're using, a linear inverse model, or LIM, and then go into results about precipitation in Southwest Asia and how processes like the El Nino Southern Oscillation and the Madden-Julian Oscillation can lead to periods of enhanced subseasonal skill, which is really, really important and helpful for FuseNet. So the Famine Early Warning Systems Network was founded in the mid-'80s in response to terrible famine in East and West Africa, and I believe it's been going in some form ever since. So it's located within the US Agency for International Development, and we are on the NOAA side here. There are lots of other collaborators working on the weather and climate monitoring and outlook part of this food security problem. So for instance, my office mate is on the NASA side. And here's just an example of some of the types of reports that FuseNet offers on its website and is disseminated to lots of different stakeholders like the World Health Organization and so forth. So it's very much created to be adaptable to respond to emerging crises and give actionable information at the time it's actually needed. So if you go to the FuseNet website, fuse.net, this is what's on the front page. It's a very sobering map of acute food insecurity in all these different colors. There's different levels of that insecurity. And the only countries that are shown are the ones that FuseNet is actively working with and has an agreement with to help with food in that country. So that's why not all of them are filled in. And clearly you're drawn to the Horn of Africa region, which is going through a really bad crisis right now. Afghanistan up here similarly is in a crisis level, but there is some good news. These black exclamation points are showing all of the areas where food insecurity would be one level worse without humanitarian assistance. So this is, you can think of these areas as large quantifiable amounts of food assistance being given out and really making, ameliorating that food insecurity. So right below that graphic, there's this discussion of the areas of greatest concern, and I'm just showing this to highlight the kind of role that weather and climate information has here in relation to other things like violent conflict or food prices and macroeconomic variability. So these yellow boxes are showing all of these specifically climate and weather information that's affecting security and food security. So the Horn of Africa in particular, it's been going through this really unprecedented period of lots of consecutive failed rainy seasons, unfortunately. So there's lots of problems there with drought and a lack of rainfall. And then not too far away in South Sudan, it's a problem related to more flooding, and that happening for the 4th consecutive year. So this is just to give you a sense of the scale of how important the weather and climate information is relative to all of these different factors that affect food security. So I'm just going to briefly go through, in my 2 years working for FuseNet, how my outlooks that I create and that we'll be looking at later, how they're actually brought into this whole question of humanitarian food security and creating forecasts of what food security is going to be like. So once a month, the food security analysts who have had some training in how to interpret weather and climate information, they provide working assumptions on a range of timescales. They change every month depending on what part of the season you're in, what's happening. And then a whole group of regional scientists. So there's a regional scientist for Southwest Asia. It's actually my colleague, Andy. He and they respond to these assumptions and can either affirm the assumptions based on current forecasts of things like ENSO and just all these different tools that we have on subseasonal or seasonal timescales mainly. And yeah, they can either decide to confirm the assumptions as they were written and provide evidence for that, or they can provide evidence for why they want to modify the assumptions as they were written. So that's a bit of individual work. And actually I'm sort of a sub part of this, where my subseasonal outlooks are one of the pieces of information that the regional scientist, in my case, Andy, uses to make his decisions about how to change these assumptions or not. And then once a month, we all get together. So all the regional scientists and all the support people like me can chime in too. And there's a seasonal forecast review where we go region by region and show what the assumptions were, why we want to change or keep them the same, and then show everybody else who hasn't seen the outlooks for that area yet. Everyone gets to take a look and pretty much confirm, yes, we're all seeing the same sort of, same sort of likelihood of precipitation or drought or whatever that the individual regional scientists saw. So it's a bit of a scientific group discussion that's all geared towards creating a final version of this presentation that's presented the following day to a different group of people that more involve food security analysts. So there's sort of this intermediate meeting and then a more final presentation to a different group of people to ask their questions about what these weather and climate forecasts are telling them. And then they assimilate all sorts of information, the macroeconomics, political instability, whatever else is going on in that area that's going to affect food and moving food around. And then that's how resources are positioned based on these scenarios that are developed, and eventually a most likely scenario is determined, and then food and resources are moved. And then just going back to that first graphic here, first we were looking at the near term sort of monitoring timescale, and then you can also switch the button to look at a farther looking, a few months in advance forecast, which is generated how I just described. So my focus again is just one part of this, to create subseasonal forecasts, and really their outlooks. We give probabilistic information about precipitation over Southwest Asia, with, again, centered on Afghanistan, and to also understand what our sources of predictability are in that region. So first, I'm just going to briefly introduce what the current state of subseasonal precip forecasting is. What does subseasonal mean? How does it compare to skill at different time scales? And then we'll get into some results. So the main story is that subseasonal forecasts are not great. This is a map showing forecast skill on the y-axis, and then different time scales and lead times that you're making your forecast on the x-axis. And first, at the shortest lead times, we have weather, synoptic, time scale variability, with forecasts being really quite quite reliable at short lead times, given that dependence on your initial conditions. And then that deterministic skill, though, drops off quite rapidly at about 2 weeks. Then if we go to this longer time end of the diagram with climate projections and seasonal forecasts, those are also good to fair in terms of their skill. These are more dictated by boundary conditions like sea surface temperatures and other types of low frequency forcing, which can also generate predictability on seasonal or longer timescales. And then in the middle here, we have subseasonal forecasts where maybe at week 3 or 2, depending on your definition of subseasonal, you have some okay skill. I guess we're in the fair range here. And then that skill rapidly drops off to just absolutely terrible by the time you're at week 8 or something like that. So this is known. This is because at this time scale, you have some information from the initial conditions being important, but that importance has diminished. And your boundary conditions are also just not having quite enough time to give you a really, really reliable signal all the time. Another map showing this for precipitation, sorry for the postage stampy here, but this is an evaluation of precipitation forecast skill using anomaly correlation coefficient, ACC, where you just correlate your verification with your forecasts, and at every grid point get maps like this. And this is for the broad winter season. And this is just considering the skill in about 5 of the S2S models. The S2S it's a collection of subseasonal models that are evaluated together. And you can see here that as you increase the lead time for any one of these models, that precip skill, particularly over land, where we care about it a little bit more, is diminishing quite rapidly, so that by week 6 here, if you try to find plot contours with any contours on land, it's a little bit hard to do so, although Brazil does stick out as a region that does have some skill here. So generally, there's just not, on average, really useful skill in these models for precipitation. Precipitation sticks out as a very, very difficult variable to forecast. But I did just want to circle here, the ECMWF model does have some skill, generally over Southwest Asia and parts of Northern India, it looks like, which is good because that is the region that we are caring about. So instead of being really bummed out that we can't have good subseasonal forecasts all the time, there's been a movement towards identifying the smaller amount of forecasts or forecasts of opportunity that are characterized by an elevated predictable signal to unpredictable noise ratio that reflects just higher confidence in that forecast overall. So these forecasts of opportunity can often be related to slowly evolving tropical heating anomalies, which can generate a Rossby wave source and a response in the extratropics, particularly related to ENSO and MJO. And I'll go into why in this region in particular we're focusing on these two. But for lots of different areas around the globe, these two tropical phenomena can lead to a predictable signal that, if you see it coming in your initialization, can give you enhanced skill several weeks out, which is what we will see. And just to reiterate, this is a small fraction of all forecasts. We're going to look at 20% of our total number of forecasts and consider those our forecasts of opportunity. And here's just an example of one that we saw coming when we had first started getting these real-time subseasonal outlooks going for FuseNet. So this is actually one of the outlooks that we pass over to food security analysts in those monthly meetings. And this is reflecting for a week 3 forecast that was initialized in mid-December in 2021, that we have an above average likelihood, or we have an enhanced likelihood of above average precipitation. So again, we're highlighting the probabilistic nature of the forecast that we're giving on these lead times. And we will get back to why we had a forecast of opportunity at the end of the talk. So the research questions I'll be addressing for the remainder of the talk are: first, can we objectively identify subseasonal forecasts of opportunity for winter precip over Southwest Asia? And if we can, then what phenomena are associated with those periods of elevated skill? And so just to introduce, I've been highlighting ENSO and the MJO, I wanted to introduce why. So there's some past research that has found that El Nino conditions on average, this is a November to April mean anomaly of precipitation. El Nino is associated with enhanced precip over the region. La Nina is associated with anomalously low precipitation. The 1999 to 2001 La Nina was associated with a really strong drought in this region. And we've had some ongoing drought the past few years, although it's unsure if this season might take us out of that or not. We'll see. But yeah, La Nina definitely has that influence. On more subseasonal timescales, the MJO has also been found to have a relationship to precipitation in this area. So these top two panels are showing different phases of the MJO. So the MJO is a propagating feature. In these earlier phases on the top left here, 2 to 4, you have a big negative outgoing long wave radiation anomaly, which is signifying enhanced convection in this area. And what that ends up doing is creating an upper level anticyclone over Southwest Asia, which is actually shown by this positive OLR anomaly. And then that leads to anomalous subsidence and negative precip anomalies during these early MJO phases. Conversely, as the MJO transitions from 2 to 4 to these phases 6 to 8, it's propagating across the maritime continent and into the North Pacific, so you can kind of see there. And then there's a big positive OLR anomaly signifying suppressed convection that forms afterwards in the Indian Ocean. And that has the opposite effect at upper levels and on the vertical motion over Southwest Asia, so that you have anomalous enhanced precipitation during these later phases of the MJO. Okay, so that's our background for why we're going to be focusing on these two processes, why we think that they are leading to forecasts of opportunity in this region. Now I'm going to switch to methods, what tool we've been using to generate forecasts. It can also be used as a diagnostic tool to understand sources of predictability. So I'll touch on a dynamic way to do that at the end. We haven't employed it for Southwest Asia yet, but that's our next step, we hope. So this linear inverse model, we started with this tool. FuseNet doesn't care what tool I use. So, but we picked a limb for lots of reasons here. First of all, it has had a history of success with subseasonal forecasts and diagnosing sources of predictability on subseasonal timescales for other variables of interest, where first it was attempted for 500 geopotential height, then NAO, and then most recently North American 2-meter temperature. And now we can say that we're also successful with precip. We like the limb as well because there is a way that's consistent with how we generate our forecasts in this framework to anticipate, to measure that signal to noise ratio, and therefore anticipate our forecasts of opportunity. And that's how we get the probabilistic information that I showed previously. And this is information that we can get at the time we're making our forecasts, and it's really not computationally very intense or anything. I mentioned also you can use the limb as a diagnostic tool. And then finally, it's very computationally friendly. I did all of my training and running the forecast and the cross-validation and everything on my laptop that I'm using right now. So what the limb actually is based on is this equation here, which I'll explain, but you first start with creating a state vector X, which has whatever combination of variables in it that are going to best represent the state of your system. So if you wanted to study North Atlantic SST variability, you wouldn't have these variables, you would pick, different ones. So what we've selected in here are precipitation and 2-meter temperature just over a regional box over Southwest Asia. And then so those are our target variables. I'm just focusing on precip in this talk. And then we have these 3 other ones, 200 millibar stream function over the Northern Hemisphere to get a measure of hemispheric circulation variability, and then tropical outgoing long wave radiation and sea surface temperatures, which are providing our information about the sources of predictability we think are important, namely ENSO and the MJO heating. And also just, these are not indices or anything. So there's the possibility that other types of heating variability that aren't captured by purely Nino 3-4 or something like that, are also being included in our model because just because of the way we've defined it. So the idea is that these regional target variables are going to be able to, we're going to be able to train our model to learn relationships between our regional target variables and these large scale predictors. And we're using JRA 55 reanalysis products, except for precipitation, which is from CHIRPS. That's what our partners at FuseNet use the most. It's a satellite-derived combined gauge satellite product. And we're taking daily anomalies with a 7-day running mean applied that should be JFM, for JFM for this 40-year period. And so you create your state vector. And what we do in practice to make this a tenable matrix to work with is we truncate each of these variables based on using EOF analysis, where we retain enough variables to keep the majority of the variance of each one of these. Sorry, we keep enough principal components to retain the majority of the variance of each of these variables. And then we use the principal components that we kept to build our model. And the limb is, again, based on this assumption that we can model our evolution of the state vector in time as having a contribution from this slowly evolving predictable component represented by this operator L, which acts linearly on X, which is why this is called a linear inverse model. And then there's also a contribution to the evolution that's coming from fast, rapidly decorrelating, and therefore unpredictable variability. And so we don't actually use this to make our model. We want to isolate the slowly evolving predictable part. And in our framework, there's a time scale separation we're sort of making here. So we're using our 7-day running mean anomalies and weekly variability that's isolated that way to represent slow and predictable, and fast, unpredictable is representing shorter timescale variability, like synoptic timescales and things like that, which is actually what I prefer to study, but it doesn't help us forecast, so we don't think about it here. It's been shown that you can create your operator by taking the lagged and instantaneous covariance between all of your variables, so just in between all of your principal components that you retained. And here the lag that you pick is non-trivial to decide. There's a whole way of figuring out what lag to use for this. Here we're using a 5-day lag, which has been used quite a lot. And then once you have your operator, all you need to do is solve the homogeneous part of this equation here and get an equation for your state vector at some forecast time t, just by knowing the initial conditions x of 0 and then taking the exponent of this operator. So this is how we can get a forecasts from a 1 to up to a 42-day lead time using the same operator there. And then once we have L, we can also use that to determine this expected skill metric, which is a function of the limb signal to noise ratio. And the signal to noise ratio is a function of the forecast covariance and then the error covariance. So it's two terms that we can determine in the consistent framework of the limb. And so this gives you a time series. The way we're defining it gives you a time series for every forecast and every lead time of what the limb thinks its skill is going to be. And so you can use that, and what we do is take the 20% of initializations that were initialized with the highest expected skill. So when the limb thought its forecasts would be really, really skillful, the most skillful in the group, how does the skill of that subset compare with the skill of the remaining forecasts? So that's how we will be considering our SFOs, is with this expected skill metric, which is consistent with our linear inverse model. All right, so going to results here, this is showing that same metric as before, anomaly correlation as our skill metric. This is for weeks 3-4 average forecasts. And on the left here, we are assessing our skill for all dates in our record, which again was 1981 to 2020, January to March initializations. And we see, and again, Afghanistan's right here in the middle, and we can see that we have skill that's plottable, which means that we are, if we do a loose comparison to that prior skill that I looked at before in the S2S models, that means that we are comparable to or beating the skill of the other subseasonal models. So the LIM's in the running when it comes to how other subseasonal forecast models are doing. So this is all dates. Again, anomaly correlation to be considered really skillful or useful, you have to have regions or values more above 0.5. So that's not quite what we're getting just with all dates. And that wasn't surprising to us. These three right panels now are three different ways to subset the forecasts using different indices. So this panel B is what I just described, using the LIM expected skill when it thought its skill would be good. And for that 20% of dates, you do see big skill increases that are statistically significant, shown in the dots. And so that confirming that the LIM actually was able to anticipate the forecasts that would be more skillful. But we were wondering, do we have to go through the bother of creating a LIM and creating this expected skill variable? Maybe if we think that our subseasonal forecasts are ultimately related to ENSO and the MJO, maybe we can just use indices of those two phenomena to anticipate our forecast, and maybe those will be skillful too. So we tried that with the Nino 3.4 index to represent ENSO, which isn't perfect, but it's widely used and widely available, so we tried it. And we just took the 20% of dates with the highest amplitude Nino 3.4. So combining La Nina and El Nino, and you don't see any broad scale increases in significantly different skill when you just do this. And this is also the same as if I broke it down into just La Nina or El Nino, you get similarly looking maps, just as a note. And then we also tried this using, should say the RMM, it's the RMM index we're using for the MJO. And we just tried taking high amplitude values of that, top 20%. And again, we don't see any significant skill increases that way. And that's also holding for if we broke this down into the strongest phase 2 to 4 or 6 to 8 MJO phases as well. But we know that the ENSO and the MJO both have an impact on precipitation in the region. We still think that these two phenomena are related to the expected skill. And we're going to investigate that further. And I do just want to say that I'm not trying to, hate on these two indices. Neither of these indices were determined to have this application, right? These weren't created to make precipitation forecasts over Southwest Asia. So in a sense, it does make sense that our expected skill is doing the best job here because it was specifically tailored for this task. Oh, and just to show weeks 5, 6 skill as well, this idea still works where we have significant increases in skill during those high expected skill dates. Our forecast of opportunity, that idea is still working. The area has shifted though now to farther in the south. And we see that there's a bit of an increase in the skill that you get from Nino 3.4, and it's roughly in some of the same areas as our expected skill. So at weeks 5, 6, it looks like the LIM expected skill dates are more lining up with strong ENSO dates, and the MJO becomes less important at such a long lead time. So I did say though that we know that ENSO and the MJO are related somehow to precipitation in this area, and we thought that they're related to our predictability. So we just want to investigate this relationship between these dates that expected skills picking out versus ENSO and the RMM. So this is just to show the difference in the temporal variability of the expected skill dates. The high expected skill dates, our forecasts of opportunity, are in all these dots. And then the low expected skill dates are in the gray lines. So if you pick any year, really, and so we were going here from 1981 on the bottom, moving along in time down to 2020 up here at the top. And then we're going from January to March for each of these years. And if you just look at the dots and the lines for a specific year, you can see that you can go from the LIM having high expected skill dates to low expected skill dates and then back to high. There are a lot of different processes, not just ENSO or the MJO, that's affecting the predictability of precip in this area. You can have internal variability that's affecting things. You can have constructive interference between the heating of ENSO and the MJO. And so all of these different processes are affecting precipitation on a range of timescales. And the limb is able to capture that, and it has, as a result, pretty high temporal variability. And you can contrast that to what's in the fill, which is the Niño 3.4 index for the same exact time. So you can tell, first of all, that Niño 3.4 is a much more slowly evolving field than our expected skill. And that's why we think it's so helpful with prediction. But it's not able, it's not giving you the whole story. The constructive interference between ENSO and everything else that's going on is what was really dictating the precipitation response. But you can see, which is intuitive, that, for instance, the 1998 ENSO event here, El Nino event, has periods of forecasts of opportunity. So does the La Nina that followed it for those 2 years, although it's not just a broadband increase in predictability for the whole year or anything like that. So there are some things here that make sense. 1983 sticks out. Things like that. So there are some events here where if you would expect it, if you have a strong ENSO event, you expect a strong predictable signal, and we do see some evidence for that. So, and then if we go to weeks 5, 6 here, sorry, let's cut out. That's what this right panel is the same thing, but for weeks 5, 6, not 3, 4. And you see again, in like 2016, it did have actually an entire JFM with enhanced, with high confidence in those forecasts at weeks 5, 6. So that's the relationship with ENSO and these forecasts of opportunity does increase at these longer lead times, because you just don't have as much that's predictable on that lead time for the limb to capture, versus weeks 3, 4, where you do have ENSO and the MJO and other types of intraseasonal variations happening. Okay, if we summarize that plot by just considering or asking the question, if I have ENSO conditions of a certain amplitude, does my likelihood of an SFO increase? And so that's shown here as a function of relative risk. So this is the risk this is the chances of having a forecast of opportunity compared to the chance that you have one on any random day. So anywhere where this black line is above this 1 line means that during this phase and amplitude, you have an enhanced likelihood of a forecast of opportunity. And we do see that at weeks 3, 4, and 5, 6, that we do see increases in the likelihood of up to 2 times as likely to have an SFO during El Nino conditions. And this risk or likelihood of an SFO being identified increases as you go from weeks 3, 4 to 5, 6. And there's clear asymmetry here, where El Nino is more associated with shifting SFOs than La Nina. And I'm not quite sure about why that is yet. I think it'd be really interesting to look at that though. Okay, so now we can do the same sort of first look by eye, see what we see, and then look at the relative risk for the MJO. So we're just gonna look at weeks 3, 4 now in both of these panels, but I've split it into the phase of the MJO into 2, 3, and 6, 7. So this is the early and the late phase that impacts the region. And so I'm just plotting the RMM values for either of these phases. And the MJO is a lot more temporally variable, as is expected skill. So this is a little messier to look at, but you can spot some high amplitude MJO phases that are overlapping very nicely with the forecast of opportunity. And similarly, you can see that for phases 6, 7 here in some of these cases, although clearly it's not just like every single time your MJO is in a certain phase and amplitude, you get confident forecasts. And just summarizing that plot in relative risk terms again, looking at phases 2, 3, and 6, 7, we do see that at higher amplitudes of RMM, when you're in phases 2, 3, you do again see a shift in the relative risk towards more forecasts of opportunity being identified than random chance. And same thing for phases 6, 7 here. And there's some difference in the behavior where 6, 7 has this increase in the relative risk at lower RMM amplitudes than phases 6, 7, which more has this sort of exponential looking increase at the really high thresholds. So I'm not sure if this is sampling. There's a lot of spread here in these estimates, or if this is some true, difference in the relationship of the predictability over this area. I think it'd be really cool to try to study this more. Not sure how to do that though. Okay, so that's pretty much how we were able to corroborate our expected skill metric is able to identify when either the MJO or ENSO or other types of tropical phenomena as well. We found South Pacific convergence zone OLR anomalies also shift relative risk. So the LIM is able to figure out if any type of heating anomaly is giving us predictability, instead of just relying on one index and one phenomena to tell us about the predictability of the entire thing. Okay, so just one last thing, this is my last couple of slides, checking time here, good. And this is just going back to that example of this forecast of opportunity that I highlighted before, which was also initialized at a time when the ECMWF IFS, that's their subseasonal forecast model, was showing a similar story here with their week 3 forecast. Initialized a little bit later, but it was a multi-week event. All this green here is showing enhanced likelihoods of above average precipitation over Afghanistan right here as well. So we saw this consistency between not just the LIM, but also a different forecast model that we think is very reliable in this region, or as reliable as you can be, I should say, was also pointing towards enhanced precipitation. So these two maps were given to the food security analysts, and Andy just conveyed how we really thought there would be precipitation occurring because of this, and because of this agreement and the high probabilities. And just to show you on the left here that it did rain quite a bit. This is CHIRP's precipitation in a percentage above average. So for most of Afghanistan, you can see that there were, there was quite a lot of precipitation well above average over a lot of this area, and also farther to the south where we saw that forecast skill, that forecast confidence being elevated in those two models. And this is very consistent with when these forecasts were initialized. So this is an RMM diagram. It's a way to look at the MJO. And what it's showing you here in this blue line is what phase the MJO was in December. And the red stars are showing the initialization date of the LIM and then the IFS. And you can see that we're in phases, just transitioning from 6 into 7, and that we have an amplitude of 2. So if we go to our, chances of a forecast of opportunity under these conditions, they are shifted to be almost twice as likely during this time. So this was great. We were able to provide information that was conveyed to the analysts to make their decisions about food security, and we were right, which was really relieving because this was one of the first forecast that we gave them. So that was relieving. And this was really, really welcome rainfall amid ongoing La Nina and drought conditions. So this really stood out in the season for helping them make up for that deficit that they were in. Okay, so that is pretty much what I had to say. We were able to use LIM expected skill to anticipate precip SFOs, which was an exciting extension to this tricky variable. And we see that consistent with past studies, just linking with relationships between precipitation and tropical heating, that we do see an increased likelihood of forecasts of opportunity during strong ENSO and MJO events of certain phases. So feel free to contact me if you want to talk afterwards, or I definitely would love comments and questions now. We have a paper out on this, what I just went through, where we also have we have a third tropical OLR anomaly that I didn't talk about that also shifts the likelihood of forecast of opportunity. And if you're interested in more applications using the LIM to understand ENSO and MJO variability from a diagnostic perspective or a forecast perspective, Henderson et al. Goes through how you can use that operator that I introduced that we make our forecast from. You can actually look at the empirical normal modes or principal oscillation patterns and start filtering your state vector based on MJO related and ENSO related modes of the system. So Henderson et al. Do that for looking at P&A teleconnections. And then Albers et al. Used a different type of limb, but the same exact filtering technique to diagnose the sources of the 2020 cold air outbreak that occurred in February. It was the one that took out Texas's power grid and everything. So some very interesting results there in what part of the system was making it so cold. So with that, I will wrap up. Thanks so much for your attention, and I'd love to take any questions or comments.
Thanks so much again, Melissa, for that presentation. I put Melissa's email also in the chat if you would like to contact her after this. So feel free again to use the question feature within your go-to panel if you have any questions, or use the raise hand feature and we'll unmute your microphone so you can ask your question directly. So I'll just give it a moment if anyone has some questions they would like to get in.
Easy.
Okay, well, the email is in the chat and on the screen. Oh, we do have one question. This says, do you have any indication of whether the OLR, SST, or stream function are providing more of the predictability within the LIM?
Oh, yeah, that's a good question. That is sort of what the filtering technique that I alluded to would be able to kind of provide. What you can do there is find eigenmodes that have a strong projection onto sea surface temperatures, for instance. That is, and there are characteristics of those modes that make us confident that those are associated with ENSO and SSTs. So I want to do that filtering as a next step here. So I'm not totally sure. I'm not totally sure how to answer your question yet. I would put my money more on the heating and the SSTs though than just stream function. You know, if I just had to have either or, I would go with the tropical information, probably over just stream function itself. But for the NAO, there's a paper, Albers and Newman, it's in Environmental Research Letters. They do this partitioning and they show that most of the skill from these forecasts of opportunity for the NAO is coming from this ENSO related signal. So that I would put my money probably on the tropical information. Yeah.
Great. We have another question coming in. Did you have trouble in obtaining observation data for this study from the area? I have heard that there is a lack of data in this region, and I was wondering if you could talk a little about that.
Yeah, that is a big problem. You're definitely right. So this CHIRPS precipitant data set there's CHIRP, which is just the satellite component, and then it's CHIRP with stations or your rain gauges, that's CHIRPS. In Afghanistan, you pretty much have a pretty much no difference between the two. It's mainly all satellite derived estimates here. What I'm working on right now is a paper comparing a range of precipitation data sets over the region. And we did include the CBC gauge data, which is only rain gauges. And it sticks out like a sore thumb as not being representative of precipitation. So, and in terms of on the ground working with people trying to get assessments of what's going on, it's definitely an ongoing problem for monitoring that we don't have reliable observations. I don't really think that's going to change anytime soon, unfortunately. So we just acknowledge that we are reliant on satellite information. Yeah.
Okay, great. And we have a thank you for explaining that.
Yeah, cool.
Okay, I think that brings us to the end of our time today. Again, feel free to reach out to Melissa with any questions that you have. And thank you for joining this webinar. The recording of this webinar will be posted on the Climate Program Office website within the next couple of days. And we will also post future webinars in this series on our page as well. So thank you again, and thank you, Melissa, for presenting.
Cool. Thanks, everyone.
Thanks. Bye.